Welcome back. Today we're exploring one of the most important concepts in modern LLM development, the distinction between pre training and fine tuning.
Understanding the difference between these training strategies is key to understanding how LLMs are built and deployed.
Let's start with pre training. What exactly happens during this phase?
Pre training is the initial large scale training phase where the model learns general language understanding from massive amounts of unlabeled text. This is self supervised learning. The model learns without explicit labels by predicting parts of the input from other parts. For decoder models like GPT, the pre training objective is next token prediction. Given a sequence of tokens, predict what comes next.
For encoder models like BERT, it's masked language modeling. You randomly mask some tokens and train the model to predict them using surrounding context.
Pre training is expensive. It requires training on hundreds of billions or trillions of tokens, which takes weeks or months on thousands of GPUs.
But the result is a model with broad knowledge and capabilities, understanding of grammar, facts about the world, reasoning patterns, and more.
This is where the model builds its foundation. It's learning the statistics of language, the structure of the world, and general problem solving abilities.
Once pre training is complete, you have what's called a base model or pre trained model. But this model isn't yet ready for most applications.
Right, base models can generate text or perform some tasks, but they're not aligned with user intentions. They don't reliably follow instructions or behave safely.
That's where fine tuning comes in. Fine tuning is additional training on a smaller, more specific dataset to adapt the model for particular behaviors or tasks.
The key difference is scale. Pre training uses trillions of tokens. Fine tuning typically uses millions to billions of tokens, orders of magnitude less.
Fine tuning also uses a smaller learning rate. You're making adjustments to an already trained model, not learning from scratch.
Let's talk about different types of fine tuning. The most common for modern LLMs is instruction tuning, also called supervised fine tuning or SFT.
Instruction tuning trains the model on pairs of instructions and desired responses. For example, translate this sentence to French followed by the correct translation.
The model learns to follow instructions and respond helpfully. This transforms the base model into an assistant that can perform tasks on demand.
The instruction tuning dataset typically includes thousands of different task types, question answering, summarization, creative writing, code generation, and more.
The diversity of tasks during instruction tuning helps the model generalize to new instructions it hasn't seen before.
After supervised fine tuning, many models go through another stage, reinforcement learning from human feedback or RLHF.
RLHF uses human preference data to further refine the model's behavior. Humans compare different model responses and indicate which they prefer.
This preference data is used to train a reward model, a classifier that predicts which responses humans would prefer.
Then the language model is fine tuned using reinforcement learning to maximize the reward model score while staying close to the supervised fine tuned model.
The algorithm typically used is PPO, Proximal Policy Optimization. It updates the model's policy to generate higher reward responses.
There's also TRPO, Trust Region Policy Optimization, which is similar but uses different constraints.
RLHF helps with things that are hard to specify in supervised data, like being concise, avoiding harmful content, or admitting uncertainty.
More recently, there are methods that skip the reward model entirely. One popular approach is DPO, Direct Preference Optimization.
DPO optimizes the model directly on preference pairs without training a separate reward model. It's simpler and can be more stable.
There's also IPO, Identity Preference Optimization, and ORPO, which are variations on similar themes.
Another approach is RLA, reinforcement learning from AI feedback, where AI generated preferences are used instead of human preferences. This can scale more easily than collecting human feedback, though there are questions about whether it introduces biases from the AI labeler. Let's talk about domain adaptation, which is a specialized form of fine tuning.
Domain adaptation is when you take a general model and specialize it for a particular domain like medicine, law, or code.
This often involves two stages: continued pre training on domain specific unlabeled text, followed by fine tuning on domain specific tasks.
For example, to create a medical LLM, you might first do continued pre training on medical textbooks and journals, then fine tune on medical question answering datasets.
Continued pre training helps the model learn domain specific vocabulary, concepts, and reasoning patterns without losing general capabilities.
The key is to use a small learning rate and not train for too long to avoid catastrophic forgetting of the general knowledge.
Now, what about multitask learning? How does that relate to fine tuning?
Multitask learning is when you fine tune on multiple tasks simultaneously. You mix together different task datasets and train on the mixture.
This can improve performance on all tasks by finding shared representations and preventing overfitting to any single task.
T5 is a great example. It was trained on a mixture of supervised tasks, all cast as text to text problems.
Another training strategy is self training or self play, where the model generates its own training data.
For example, you might have the model generate many responses, select the best ones using some criteria, and then fine tune on those selected responses.
This can help the model improve iteratively, especially for tasks where it's easy to verify correctness but hard to generate examples.
Let's discuss some practical considerations. How do you decide how long to fine tune?
You typically fine tune for a small number of epochs, often just 1 to 3 passes through the data. Too much and you risk overfitting.
You monitor validation loss or performance on a held out set. When performance stops improving or starts degrading, you stop.
The learning rate for fine tuning is usually 10x to 100x smaller than for pre training. You're making small adjustments, not large changes.
There's often a warm up period followed by decay, similar to pre training but on a smaller scale.
Another consideration is data quality. For fine tuning, quality matters more than quantity.
A small dataset of high quality, diverse examples can be more effective than a large dataset of low quality or repetitive data.
This is why many organizations put significant effort into curating their instruction tuning datasets, ensuring coverage of diverse tasks and high quality responses.
There's also the question of whether to fine tune all parameters or use parameter efficient methods.
Full fine tuning updates all parameters. Parameter efficient fine tuning, or PPIFT, only updates a small subset.
Feed methods like LoRa, adapters, or prompt tuning can achieve good results with much less memory and computation. We'll dive deep into these in a later episode.
One risk with fine tuning is distribution shift. If your fine tuning data is very different from pre training data, the model might degrade on general tasks.
Some practitioners mix in general data during fine tuning to maintain broad capabilities while adding specific skills.
There's also the phenomenon of exposure bias in autoregressive models. During training, the model always sees correct previous tokens, but during generation, it sees its own predictions.
This train test mismatch can cause compounding errors during generation. Techniques like scheduled sampling try to address this by sometimes feeding the model its own predictions during training.
So, to summarize, pre training builds general language understanding on massive unlabeled data using self supervised objectives. Fine tuning adapts the model for specific tasks or behaviors using smaller supervised datasets. Instruction tuning teaches models to follow instructions. RLHF and DPO align models with human preferences, and domain adaptation specializes models for particular fields.
The combination of pre training and fine tuning is what makes modern LLMs so versatile and powerful.
Next episode, we're diving into scaling laws, the mathematical relationships that govern LLM performance.
Thanks for listening.
Until next time, keep learning and stay curious about AI.